Okay, so I've got a spool, 500 kilograms, radius of gyration of 1.3 meters. It's on this conveyor belt, okay? Coefficient of static friction, kinetic friction given. Conveyor belt starts accelerating to the left at 1 meter per second, okay? So it says, hey, let's find the initial tension in the wire. Yeah, so let's do that, okay? And the angular acceleration of the spool. So, of course, we're going to start with a free body diagram, as we always do. Okay, so we're going to take our spool, draw it here like this, here like this. It's going to have a weight to it, which again is going to be 500 times 9.8. It is going to have a tension like so to the right. It is going to have a normal force up. Okay, and then again, that conveyor belt is moving to the left, so it's causing friction to the left, like so. Okay, and essentially what we're trying to do here is find the angular acceleration of the spool. Okay, so we got that. So let's go ahead and sum the forces in the x direction. Okay, because if acceleration will be horizontal. So there you have it. So the acceleration in the x direction. So I've got t minus f equals the mass times the acceleration. So that's going to be 500 times the acceleration of point G, of the center of that thing. And again, I'm going to play it stupid, say I don't know what direction acceleration's in. We'll assume positive. It could perhaps go either way depending on what happens here. So we'll find out. Okay, we'll just say it moves to the right, or we'll just assume positive, right? Because again, x and y axes will be like that. So now I'll sum the forces in the y direction. I'll have n minus 4,900. That is the weight of this guy. Okay, the acceleration in the y direction is definitely 0. It doesn't bounce up and down or anything like that, so it's going to be 0 just like that. Now I'm going to sum the moments. I have to sum the moments about g because there is no point of pure rotation here. So summing the moments about g, I have 0.8 times the tension. That's going to create a positive moment, and then a negative moment of 1.6 times the friction. Okay, of course that is going to equal I times alpha, where I is the mass of that'll be 500 kilograms times r squared, or not r squared, excuse me, the radius of gyration squared, okay, times alpha. And again, I'm playing it stupid. I'll just say alpha is alpha. We'll relate alpha to whatever I need to relate it to in a little bit, and actually that's going to be a bulk of the problem that we're trying to figure out here. So let's figure out how many unknowns I've got. 1, 2, 3, 4, 5 unknowns. All right, so we've got to start solving this thing. Okay. First thing I'm going to do is I've got to make it, with friction involved, oftentimes I've got to make an assumption. And I think the assumption I'm going to make is that this thing rolls without slipping. And then we'll prove that that happens or doesn't happen. Basically kind of solve it twice. Hopefully we won't have to solve it twice. So we're going to make this assumption. Assume rolls without slipping. Okay, so if that's the case, again, my friction will just fall out of the equation. Okay, I then have to prove that that friction is less than the maximum friction. Okay, so we don't want to forget to do that at the end. Okay, but now with that assumption, I can start relating alpha and acceleration using my relative motion equation. Basically, the acceleration of g equals the acceleration of c. Again, I'm calling c that point right there, the contact point. And again, if it's rolling without slipping, I know that acceleration of c. That's what I'm going to assume. We'll get to that in just a second. Plus alpha, again, that's the alpha that I have unknown. Again, crossed with r of g with respect to c minus omega squared r of g with respect to c. This is 0 because this sentence right here says the spool is originally at rest. Okay, and again, I'm trying to find the initial tension, initial angular acceleration, right? When it's at rest. If it's at rest, that means omega is 0. That thing goes to 0 right there. Okay, so let's go through and let's start putting in each thing that we know. Okay, so what I know about the acceleration of point G is it's in the x direction. Positive, negative, I don't know, we'll find out. Okay, but AG is definitely in the I direction. There's not going to be a Y component to G. Okay. Next thing I'm looking at is AC. This is what I know, again, based on the assumption that it rolls without slipping. I know the acceleration of C is to the left at 1 meters per second. So that's going to be equal to negative 1I. Okay. Then I have alpha cross R. Again, I don't know what alpha is. I know it's in the K direction. So I'll go plus alpha in the K direction crossed with R. This is from C to G, so that's going to be plus 1.6J. Like so. Okay, so from that, I now have a relationship between the center of gravity, the acceleration of the center of gravity, minus 1.6 alpha. This is all in the I direction, okay? But now I have the relationship. Now, there is a fourth equation. I still can't solve all of this stuff, right? Because I've only got 4 equations. I do now have a relationship between AG and alpha. The problem is that's, again, just one extra equation. I have 5 unknowns. Okay, so I need one more equation. Now, here's the thing that is definitely true. What I know for sure is about this point right here, which I'll call point B. It has to roll without slipping. So I maybe should have put the... Actually, let me go ahead and do that. Let me see if I can't screw this up. Oh, gosh. Undo. Undo. Anyway, I guess there's probably an easy way to move this down, but it doesn't really matter. Sorry. So, but what I know for sure is it has to roll. There's no way it can slip on that cord. So I'm going to write the same equation, but do it with respect to B because I know for sure it rolls without slipping on that cable. So again, I'm going to have AG equals, now this time AB plus the same alpha crossed with R, this time of G with respect to B, minus omega squared R of G with respect to B. Now, here's the thing. This is still 0. Still have no angular velocity at this point. It's still at rest. The other thing I know for sure is, again, that cable is not moving, right? There's no slipping. That cable's not moving. The contact point, there's no acceleration of this point. And again, that's because obviously it's not moving horizontally, but again, without any initial velocity, I don't have a vertical normal acceleration either. So both of those guys go to 0. Okay. Now again, AG I definitely know is in the I direction. Okay. Don't know what it is. I know it's horizontal. This has to equal then alpha. Again, I don't know what it is. It's in the K direction. And then this has to be the same idea, which is instead of 1.6, now it's just going to be 0.8, because again, it goes from B to G. So that's going to be 0.8 J. So from that, I learned that this is negative 0.8 alpha in the I direction. That's what AG is. Now I've got two equations, two unknowns. I can find AG and I can find alpha, right? So the AG equals 1. Alpha then equals negative 1.25. Now, I don't know if these are true because, again, remember I made this assumption that this thing rolls without slipping on the conveyor belt. Okay, so for that case, I know this to be true. Okay, I know the alpha and acceleration for that case. Now that I know that, I can go in and solve for my other unknowns here. And when I do that, I find that my T equals 2320 newtons, and my F equals 1820. Okay, but now remember, I have to prove this, right? I have to prove that it rolls without slipping, which basically means I have to make sure that that friction force does not exceed the maximum possible friction force. And that maximum possible friction force is 0.5 coefficient of static friction times the normal force, which is 4,900, which we get from the sum of the forces in the y direction. And the maximum friction force is then 2,450, which is definitely bigger than 1820. So we're good, right? I didn't exceed that maximum friction force. Therefore, my assumption is correct. And the alpha and the tension, therefore, are correct. Now, if the friction force had been above that, then I would have known the friction force equaled the 0.4 times the normal, and then I could have solved the problem that way. Okay. Again, maybe I do it this way. I kind of circle this. This is what comes out of my assumption. I know for sure that thing rolls on the cable, so that second one is okay. Anyway, what you got to do here is, just that, right? Free body diagram, sum the forces, find a relationship between your accelerations, make assumptions about frictions, prove those assumptions, and get the right answer.